Okay, all yours, Fran.
Okay, thank you, Mati, and thank you everyone for joining. My name is Francisco Laborda, and today we're going to be talking about time complexity. I know some of you might have seen this topic at some point in your life, but probably many of you have not. So I thought it would be a good place to go over it here at the Lenio Talks. So this topic is known to be a little bit theoretical and a little bit far away from real life. So my goal today is that you get the intuition behind it, that you understand the main concepts of it, and so you know what all these things mean, even if we might not be digging into the details. So, of course, it will be an interactive talk, so I will be asking you questions at some points, and please feel free to interrupt me with comments or your own questions. Okay, so first of all, let's say that time complexity is a way of measuring the overall performance of a block of code. It can be a method or anything that you have to run. A similar analysis can be done to the code in terms of memory usage, which is called space or spatial complexity. But today we will be focusing on execution time. So our ultimate goal is to compare different solutions in terms of execution time, to be able to know which one is better, which one performs better. So first, some things to consider. Measuring actual time is a little bit tricky and difficult because it depends on the code running, other code running at the same time. Like in your computer, there's other things running when you try to measure the time of your code. Then the code can be interrupted by things that happen in your operating system. Usually you have to run several times the same thing and use the average to accommodate for these imperfections. And if the code has to run for a long time because you want to see how it scales, then it becomes more inconvenient because you have to wait for it to run. And if you compare it with another solution, well, then you have to do the same for the other solution. And maybe you don't have the code or you have to implement it to know if it will be better. So we don't want to replace benchmarks. They are a great tool. This is just a different approach. And one of the great pros of the time complexity analysis is that we won't need a computer to make the analysis. We can do it with pencil and paper, just looking at the code. And finally, this will allow us to put the algorithms in categories according to their performance. So we will know like which ones are better than others in terms of time execution time. One disclaimer, we will probably never go through a full complexity analysis on the code we write in real life. Could be too much, but understanding the basics will be very useful when we have to decide what data structures to use in our solutions. So today we will be talking about measuring execution time in terms of the input size. So how much will your execution time increase as you increase the input size? But actually, we will not measure the time per se. We will instead be counting the amount of elementary steps that your code makes. So this will allow us to make all the analysis without the need of an actual machine, as we said before. And this also means that our final result will be a mathematical function, the amount of steps for each input size. So we will not say like this code takes 10 seconds to run. We will say like, well, this is the function, the mathematical function that describes the execution time for this code. So for each possible input size, it tells us the estimated time, or let's say the amount of operations that it will make with a formula. And we will be considering the worst case scenario. That is, well, we will talk about this later, but this means that we're going to use the cases to the analysis that will make the code run the largest time. So let's go into a little bit more detail of each of these things. So first, execution time as an input, as a function of the input size. In this way, like here's a graph of different functions. This is going to be the result of our analysis. We're going to get the graph or the function that represents how much time our code will take, depending on what size of input we give it. So if we give them larger sizes, how the time will behave. Okay. So in this way, we can see how much the code will take to run for every possible input size. We do not have to focus on any particular sizes. And it gives us an insight on how the time will increase as we increase the size of our input. So it can answer questions of the type, if I double the size of the input, will the execution time double? Will it stay the same? Will it grow? How will it grow? How does my solution scale? So that's why we're going to use a function. What do we mean by elementary steps? Well, since we are not going to measure the time, we will count the elementary steps. We have to be in line with what counts as an elementary step. So for example, variable assignations, variable readings, Boolean or arithmetic operations, they all can be considered elementary steps. And loops and method calls that involve a loop, or method calls that involve recursion, they cannot be considered elementary steps because we don't know how much time they will take. We cannot say like, this is one step when it involves a loop that will take indefinite amount of time. So we'll say that an elementary step is anything that takes a fixed amount of time to perform, okay? So if we multiply the time it takes to run one step by the amount of steps that the code makes, we will get the execution time, or at least an estimation of the execution time, okay? So let's talk a little bit about the worst case scenario. So for every input size that we consider, we're going to analyze or do all our analysis using the specific input that forces our code to make the largest amount of elementary steps. So basically the tough case. We're going to use the case that makes the code do the most work. Why we do this? Well, first, let's say that finding the worst case scenario is different, can be easy or hard depending on the code. Most times it's easy, but the main goal is that we will get a warranty, which means that it will not take longer than the estimated time, because we have studied its behavior in the worst possible situation. So it won't take more than that. So this is a good thing. There are other type of analysis that I consider, for example, the average case scenario, where you consider that the input is random. It's a good analysis because it might be closer to reality, but well, if your input is really random. But this one is easier for the explanation, so we will go with this one. Every time that you hear about complexity analysis, unless they specify otherwise, they mean worst case scenario. That's the usual way people talk about complexity. So let's go through an example. Okay, so here we have a very simple code that gets an array, and it searches for a 5 in the array. So it goes through every possible position in the array, and if it's a 5, it returns that, yeah, I found it. If not, false. So first of all, we have to do what we want to do is get the function that the mathematical function that gives us for each size of input how many operations it will make, right? So first of all, we have to define what is n. We're going to write the function in terms of n. And what is n? What is the size of the input? Okay, so we will define it as the array size, of course. Second thing we have to do is define, well, what's the worst case for this code? So I'm asking you, what's the worst case? What's the case in which how is the array that we can give this code so that it has to do the most operations.
There is no 5 in the array.
Perfect. There is no 5 in the array. Like we have planned it. You worded exactly as my slide. Thank you. So if there is no 5 in the array, of course, it will have to go through all the array. So let's see which elementary operations we have here. Okay, so let me find my mouse. There you have the pointer. So let's say that assigning here is one operation, and comparing and getting the array, they are all elementary operations. The only one that is not an elementary operation is the whole loop. So we need to know how many operations are outside the loop and how many operations are inside the loop, and multiply the amount of operations inside the loop by the times the loop will have to iterate. So we can say that the first assignment is not part of the loop because it happens just once at the beginning. So that's one operation at the beginning. Then there will be one return operation at the end. That's a second. We can say 2. And then we have the return true. This will never happen. Does anyone know why this never happened?
Because it's the worst case.
Exactly, because it's the worst case. So in the worst case, we will never return true. We're just considering that case. So how many times the loop will iterate? Well, exactly the amount of elements in the array. That is n. And how many operations does it have inside the loop? Well, we can count 1 here, the comparison, 2, getting the length, 3, incrementing the variable, 4, accessing the array, 5, comparing it with 5, and that's it. That would be 5. So the formula would be 1 plus 5n plus 1, or 5n plus 2. So this is the function, and it was really easy to get the function in this case. Let's go to another example. So let's say we can assume that the array is sorted, and we can apply binary search. So we're going to do a binary search for a 5 in the array. So again, what's n? Well, n is the same as the array size, which is the worst case. Well, here we have to consider it again because it's a different code, so the worst case could be different. But it's the same. It's the same case in this situation. It's that the 5 is not there. So the code will have to go over the most amount of iterations to realize that the 5 is not there. It's equally as bad as if the 5 is in the last iteration. It would be the same. But let's say that there's no 5 in the array again. So how do we count the operations here? Well, we'll do a similar thing. We're going to see which ones are outside the loop and which ones are inside the loop. So outside the loop, we have 1 here, 2, 3, 4, 4 at the beginning, and then the loop starts. So what does this code does? Well, it starts halving the array. It cuts it in half. And it looks if it found the 5 there. If it didn't, then it just considers the left part of the array and it throws away the right part, or the opposite. So let's first count how many operations there are inside the loop, and then we're going to see how many times the loop will iterate for the worst case. So inside the loop, we have 1 operation here at the comparison, 2, 3, 4 here, 5, 6, and then 7 to access the array, 8, and it will be 9 and 10. I think I did something wrong because I had more operations before. Let me count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And this one will happen either here or here. So we just count once, okay? Because it won't do both in the same iteration. So in one iteration, it will go through this side of the if or this side, okay? So the other question is how many times. So we have well. So the other question is, how many times will this loop go? So let's take a look at what the array is doing. The algorithm is doing. So first we have the whole array like this. And in the first iteration, we are going to cut it in half. And let's say this time we get the right side. So we cut it in half. So the second time, we're going to do the same. We're going to cut it in half. Let's say that this time we get the left side. The third time, we loop. We're going to do the same. So let's say we have the right side, this part. So how many times can we do this? So if the array size originally is n, this is the complete array, how many times can we cut it in half? Well, that is the logarithm of n, the logarithm base 2 of n, because that's the amount of times you can cut a number in half till you get 1. You get 1, you finish. Either it is a 5 or it is not. You found it, you didn't find it. So this is the same as considering if you go upwards, how many times you can double a number. Well, that's the powers of 2 that you apply to that number. So log n is the amount of times the while will loop, will iterate. And we said that 12 is the amount of steps that it makes in each loop. So the formula would look something like 4 plus the logarithm of n times 12, the amount of times it will loop, times the amount of steps in each time, plus 1 at the end of the return. So let's write it like more normally, like 12 times logarithm of n plus 5. Okay? So let's compare these functions. Of course, this is not a valid comparison because they are not solving the same problem. One of them assumes the array is sorted and the other one doesn't. But anyways, we're not trying to see which one is better. We're trying to see how they behave differently, okay? So this is the calculation of the formula of the amount of operations they will make for different sizes of arrays. And you can see that a trend becomes to emerge in the right column, that it's a little bit better. It's faster, it makes less operations, even though at the beginning, the one on the left could be better. I think only, yeah, well, sometimes it's better. Okay, but what happens when it scales up? So let's say that one elementary step takes 100 nanoseconds on a computer. I'm assuming, guessing a little bit, but let's say it's a good estimation. That's like very little time. What happens when we give them bigger input sizes? So for 1K array, it will take this amount of time compared to this. And look how it starts growing. Like if we give them 1,000 million, well, a billion input size, it's starting to take 500 seconds against less than 1 second. So well, this shows us that a logarithmic solution is not better than a linear solution. It's horribly better or beautifully better. It's incredibly more efficient. We're talking about completely different orders of magnitude. So this brings us to big O notation. Maybe you've seen this. Well, you've seen it at the title of the presentation. And what does it mean? So to make the long story short, we're going to say that if the function that we are analyzing is a linear function, because the biggest term has the variable with no exponent, just plain n. So we will say, okay, let's pick f of n equal n as the function that represents all linear functions. And we're going to say that this function, the function from our code, belongs to big O of n. Or we can just say that it's a linear function. Or we can say that it executes or it runs in linear time, because the amount of time it takes grows linearly compared to the size of the input. So for our second function, 12 logarithm of n plus 5, well, it's a logarithmic function because its main term is logarithmic. So we say, okay, we pick function logarithm of n to represent all these type of functions, and we say that our function belongs to O, big O of logarithm of n, or that our code runs in logarithmic times. So same thing for if we had a quadratic function that arises from our analysis, we're going to say that it belongs to O of n squared, and it is quadratic. And if the function does not depend on the size of the input, there are cases of this, we're going to say that it's constant. For example, we have a function that it always takes 62 steps. Well, then we're going to pick f of n equal 1 to represent all those functions. And we're going to say that the function is constant, or it's also written like it belongs to O, big O of 1. Okay? The details of how these are just math, and we could go over them at some other time, but I don't think they're very useful for this talk. But it's just a way of comparing functions and grouping them into families. So most popular complexity categories that we will see on algorithms are, well, constant, logarithmic, it's also called sublinear, linear, quasi-linear, or log linear when you have an n multiplied by a log n. This is in between quadratic and linear, because if you look at this, log n is always a number between 1 and n. So if you're multiplying n by a number between 1 and n, it's not going to be quadratic, but it's going to be more than linear. But it's usually a quite efficient time. Quadratic is efficient, but sometimes it's too much for some use cases. Then you have cubic. Any exponent will say it's polynomial. And then you get into exponential times, and that's things that are very inefficient. Let's say that some problems have their solution in one of these categories, and sometimes it's proven that you cannot make it faster than that. Like if you want to print an array in the console, well, you cannot do that faster than linear because you have to print n things. So it's going to be linear. And for every problem, sometimes they can find which is the best way of doing it. Or maybe you have to choose what data structure to use, but we'll get to that in a moment. So this is how they look on a graph. So if you see logarithmic solutions are way better than linear ones, but linear ones are way better than sublinear ones, log linear ones, and so on. They are in different categories and different orders of magnitude. So if you have a code and you know that it runs here, then having a solution that runs here will be way better. Even though for small sizes, it might not make a difference. It will be the same. But complexity analysis makes sense when we're talking about scaling, where we're talking about big numbers of n. Okay, it doesn't matter what happens at the beginning for the complexity analysis or for the big O notation. It matters what happens after a certain point, after you get big enough with the size of the input. So how does this relate to real life? Let's say, well, usually we won't do it, as we said before, with our code, but we have to know that the code that we use, that we get from libraries or the language that we're using, and it gives us, for example, arrays or maps or sets or any other structure that we're going to use, we have to consider that their operations, they have a complexity function associated, and they fall into a category. So depending on what we're going to do, we have to choose wisely. So we're going to ask questions like, what is the temporal complexity of the insert operation, or the access, or the remove? How long will it take to add another entry into this object? Well, does it depend on how many entries are there before? So what would be the worst case? is there any data structure that will allow me to do it faster, or how fast? So here I found a nice table. I borrowed it from bigocheatsheet.com. And it's really nice because it shows orders of worst case and average cases for different data structures. So let's take a look at the array. Well, array access has constant time. It doesn't matter how big the array it is. If you want to find the position, the element at position 75, you're gonna get it in constant time. The reason is because arrays are implemented in memory all together. So you don't have to search for it. If you want the position 75, you just make the calculation of where it is, and the code will find it. But if you have to search for an element that we don't know if it's there, well, that's linear, as we saw before. For insertion and deletion, we might have to discuss a little bit more to understand why they are linear. Well, the reason is that it's the worst case. So the worst case is you run out of space in the array. This is transparent for us when we're coding because there's layers of abstractions that will solve this for us. But the time that it will take is linear, because if you run out of space in the array, what the layer before that we'll have to do is copy the entire array into a different position in memory where there's more space for your addition. And deleting one is also linear, because if you want to let's say you had to remove the element at position number 3, well, you cannot just block that position and say, okay, fine, this position is not available anymore, because then accessing won't be constant anymore. If you do that, then position number 3 could be invalid. So then you didn't access it in constant time. You have to go to position 4, but maybe position 4 is also deleted. So you start having a not constant access. So deleting is linear because you have to copy the entire array so that position number 3 is not there anymore. Okay. Of course, there's tricks that you can implement to make things better. But this is the worst case for a simple array. Okay. So I wanted to talk about trees a little bit. You can see that trees, there are many types of trees. This is insane. Each of them have their own complexity and its own difficult parts of the code. I don't know if you had to implement any of these at university or anywhere. They are quite painful. But they give us mostly logarithmic times for everything. So this is quite good. But in reality, what we use the most is hash tables. Hash tables have this magic that even though in worst cases they are linear, all of the operations take linear time. They have to go through all the elements in the hash table. Well, in average, they run really fast, and it's considered to be constant time. So what do hash tables do? Well, I think we can talk about hash tables in another talk if you're interested. They are very clever data structures. And yeah, we'll leave it for another time. So finally, let me talk a little bit about the difference between abstraction and implementation. So abstraction is one of the most powerful concepts we have in programming, I say, because it lets us ignore the details of a code and use it knowing it will work correctly. So if we grab something that, let's say we grab a set and we're going to use it, well, it behaves like a set. Its semantics, its meaning is that the operations will do what I know they will do. But then how it really runs, when you have to run it, you need actual codes for those operations to run. And those are the implementations. So the same set could have different implementations. In some languages, you can pick which implementation you're going to use when you use a set, for example. You can have the set implemented over a hash table, or you can have the set implemented over a tree, for example. And they will have different orders of complexity for their operations. So depending on which implementation we choose, the time complexity will be different or could be different. So if we're worried about performance and scaling, we have to choose the implementation that works better for our needs. So finally, I wanted to show you a snippet I extracted from the ECMA script, the documentation. And let's see if we understand what all these words mean based on what we have been talking. So it says, it's talking about the map object. It says that it must be implemented user either hash tables or any other mechanisms that on average provide access times that are sublinear on the number of elements in the collection. So basically it means that if the number of the elements of the collection is n, and it's talking about average case, however you want to implement it, it has to be better than linear, okay? So what this documentation is talking about is specifying, is only intended to describe the required observable semantics of the map object. It means this documentation is talking about how the map should work, what its operations have to do. But it's not intended to be a viable implementation model. Like, you can do whatever you want inside the abstraction. But however you implement it, it has to follow these restrictions of complexity. So as a recap, what we've done is estimate the execution time as a function of the input size. We did that by counting the amount of elementary steps and figuring out what the function is, what the formula is. So for each input size, we have a number. And once we get the function, what we do with it is we can estimate the actual execution time, but what is more important is that we can know to which performance category that function falls into. So we have a very fast idea of how good it is compared to others. So in this type of analysis, we focused on worst case scenario. There's another case that I wanted to mention. On top of average case and worst case, you have amortized case, which focuses on the sum of many operations. So for example, if you want to solve a big problem, you might not worry that individual operations take long as you know that when you sum them all, it won't take that long. So maybe you will find a data structure that will guarantee you that if you execute the same operation like 100 times, well, maybe one of them will take long, but the other ones will run really fast. Like, one might be linear, but the other ones will be constant. So in amortized case, you say, okay, we sum them all together and we divide by the amount of operations, and we get that each of them seems to be constant. So it's an interesting analysis. It's called amortize. I think the term comes from financial analysis, but we use it here as well. So, well, that's it. Thank you very much for joining. And if you have any questions.
That was a great talk, Fran.
Thank you.
What questions do we have for Fran? Nobody is going to show some code and ask what is the data structure that they need.
I have a question.
Yes, go for it.
Just a quick question. Great talk. Do you have some recommendations about this topic? I mean, books, videos, or articles?
Depending on how deep you want to get into, I recommend you not to read about this on Wikipedia, because it gets very technical very fast, and there's no point in that. So I can send you some videos. There's great explanations in YouTube, very intuitive. And then if you want to get deeper into it, yeah, I can find some books and stuff. If you've never seen this topic in classes, then depends on how much you want to get into the math. But it's really interesting. It's really interesting. I'll send you something.
Okay. Yes, I've been reviewing this topic in the course from called Stili in Udemy. I recommend you guys if you can check it. But okay, thanks.
Cool. Great. Any other question?
More than a question, I just want to say again, like this was a great talk, and I think it's a really important subject. And even if it looks a little bit technical, some things, I think that it's really useful to know, at least for example, like for the day-to-day, how map work and how array works. This table that Fran was showing. That is really important to know, because when you get a lot of data you have to process, it can make a huge difference if you are, I don't know, for each item searching for something else that you have to assign, like to use the correct data structure there. And it's not difficult. Like it's only about choosing what is the data structure to use.
Yeah, for example, if you have to, in your situation, you have to do many inserts and not that many searches, then maybe one data structure is better at inserting really fast than searching. So if your use case is not the typical one, maybe your data structure is not the typical one. And of course, this doesn't apply when you want to be you want to optimize a code that you want to run really fast for very small input sizes as well. If you want to make that kind of optimization, you will have to go into the details and see how you can do everything really fast. And that doesn't apply to this kind of analysis, but it's also valid. This only makes sense when you have big amounts of data, or not that big, but big enough.
Yes, and I also wanted to bring something to the table that is like kind of related to this talk, that the input size, as Fran said, like as it shows, it makes a lot of difference. In one project with Juan Cruz, we had an issue that it was taking tons of times, and we couldn't modify the algorithm, so we couldn't play with different orders. And Juan found a way to actually reduce the input size like by an order of magnitude, and that was another way to actually make the application be viable.
Really? I don't remember. Which was it?
Yeah. the one that. Yeah, the maps that you reduce the data points in the polygons.
Yeah.
And like just by a simplification, because of how big was the screen to show it and the zoom that they were going to be able to do. So there were tons of points, and that was the problem. And there was an application that reduced it without any loss of, let's say, resolution, at least to the eye. But the algorithm was like working at the left of your curve that you show, Fran. So things were working.
Well, that's really clever. If you cannot reduce the amount of operations, then you can reduce the input size. That's interesting. Nice.
Okay, if we don't have any more questions, I think thanks a lot, Fran. This was a great talk, and thanks everybody for joining, and see you next week.
Thank you. See you next week.
Thank you,
Fran.
Have a good one. Thank you.
Bye-bye.
Thank you. Great talk.
Bye.
Thank you.